Hi guys, Audrey here. So today I'm just going to really briefly remind us of how to do the derivatives of the inverse trig functions. So I've got all of our derivatives written over here in the form of the inverse trig function of x over a. We're just going to pick two of them and do them. I'm going to do arcsine because that one doesn't have that extra a on top. And then I'll also do arcsecant just to show where that a sort of comes from. So we're going to look at y is equal to arcsine of x over a. And our goal is going to be, we want to find y prime. So in other words, y prime is equal to the derivative of arcsine. So arcsine of x over a prime. Well, in order to do this, we sort of have to use implicit differentiation. So the first step here is to actually take sine of both sides of this equation. And we're going to be using the fact that sine and arcsine are inverse functions. And so by definition of inverse functions, they're going to cancel each other out. So in other words, what I'm doing is sine of y is equal to sine of arcsine of x over a. And because sine and arcsine are inverse functions, when I evaluate one at the other, what's left over is just the x part. So what we have here is sine y is equal to x over a, which I could also think of, if it's helpful, as 1 over a times x. Now I'm going to use implicit differentiation to take the derivative of both sides. And because I'm starting off by thinking of y as my function, I'm going to continue that way. X is my variable, y is my function, which means when we do the derivative of the sine y side, we end up with cosine y. But because y is a function, we have a little mini chain rule that we're having to do, and we're having to pull out the derivative of y. So we end up with cosine of y times y prime. And then we're thinking of x as our variable. So if we have a constant times x, the derivative is just that constant. So the derivative of 1 over a times x is just 1 over a. Now we'll solve for y prime. To get that y prime is equal to 1 over a times 1 over cosine of y, which is 1 over a. We know that 1 over cosine is the same thing as secant, so this is 1 over a secant y. Well, now we have y prime. Awesome, except that we have y prime in terms of y. So now our goal is going to be to now rewrite this in terms of x. So we know that y is equal to arcsine. So we really could just kind of write arcsine there, have secant of arcsine of x over a. But that's not really a comprehensible answer. What does secant of arcsine even mean? It gets a little bit confusing, especially with the domains and the ranges. So we use what's called a trig triangle, or what I call a trig triangle at least. So we use this trig triangle. We're going to create a triangle that has y as our angle. So we're looking at a triangle where y is our angle. And then we're going to use our original function to kind of fill in this triangle. So y is my angle. I know that y is equal to arcsine of x over a, which means that sine y is equal to x over a. So that's what we're moving forward with. Sine y is equal to x over a. And we also know that sine, in terms of the triangle, represents opposite over hypotenuse. So that means opposite is x, and my hypotenuse is a. And then we can use Pythagoras here to solve for the other side of this triangle to get a squared minus x squared square root. So this just came from the Pythagorean theorem. Well, great. Now that we have this triangle that has angle y, I have all of the sides of my triangle, I can actually define any of my trig functions. So the one that I need in this case is secant y, because that's the one that showed up in my y prime. So if I wanted to define secant y, All we really need to know is what is it in terms of opposite, hypotenuse, and adjacent? Well, we know that cosine is adjacent over hypotenuse, so secant will just be that flipped over. So this is hypotenuse over adjacent. Well, the hypotenuse of my triangle is A, and the adjacent side of my triangle is A squared minus X squared. So now we've done our trig triangle, we've defined our secant, we can go back and write y prime in terms of x. Y prime was equal to 1 over a times secant y, which we discovered was a over the square root of a squared minus x squared. And you'll notice that those a's cancel out. So we have that y prime, which is arc sine of x over a prime is equal to 1 over the square root of a squared minus x squared, which is what we defined it to be over there. So this is the process that we follow every time in order to find the derivative of an inverse trig function. Now, just to make sure that you guys really follow, I recommend trying to do this next one on your own first, and then come back and watch just to make sure that you followed the steps correctly if you're struggling with this. So I'm going to do, I believe I said arc secant. So we have y is equal to arc secant of x over a. And we want to find the derivative of arc secant. So we're looking for y prime, which is arc secant of x over a prime. We do the same thing we did up top by taking secant of both sides. So we have secant of y is equal to secant of arc secant of x over a, but guess what? They're inverse functions. So we have secant of y is equal to x over a, which again, I can think of as 1 over a times x, if that's helpful. Okay, great. Now we know the derivative of secant. We're doing implicit differentiation again. The derivative of secant is secant tangent. So this is secant y tangent y, implicit with a little multiplication by y. So it's like a little mini chain rule that we have there. These don't all need to go in parentheses, but just to make it clear that this is 3 different things, a product of. And then we get that this is equal to 1 over a. So then y prime is equal to 1 over a times 1 over secant y tangent y, which, to make my life easier, I'm going to write as 1 over a times cosine y times cotangent y. Okay, now, great, we have y prime in terms of y. Let's make our trig triangle so that we can rewrite that in terms of x without having weird like trig functions evaluated at inverse trig functions. So trig triangle. Again, my angle is going to be that y. My original function gave me that secant y is equal to x over a. And we've remembered that secant is just going to be cosine flipped over. So that's going to give me hypotenuse over adjacent. So my hypotenuse here is x and my adjacent is a. And then same as before, we are using Pythagoras to solve for this other side. And we'll get the square root of x squared minus a squared using the Pythagorean theorem. Great. Okay, well, now I need, so I had secant y was x over a. I could have used that. I could easily just go straight from there to say that, okay, cosine y is just that flipped over. So it's a over x. But we can also see it from the triangle. It is adjacent over hypotenuse. But then we also need cotangent y. And we know that tangent is opposite over adjacent. So cotangent is going to be adjacent over opposite. So my adjacent angle here is a. I did not leave myself enough space, is a. And my opposite angle is the square root of x squared minus a squared. So that is adjacent over opposite. Let's go and plug that in over here. So we get that y prime is equal to 1 over a. Cosine y is a over x. And cotangent y is a over the square root of x squared minus a squared. And you'll notice what happened here is that because the derivative involved two trig functions, that a shows up twice in the numerator and once in the denominator, which means that we have that a left over. So that's why the a ends up there in top, whereas the derivative of sine was just cosine. So we only had one trig function. If we think about this, it also shows up in tangent. What is the derivative, or in the derivative of arctangent? This is because the derivative of tangent is secant squared, which means it's got those two trig functions, or rather the same trig function twice. So it's going to have that a two times in the numerator. So here we can finish by saying y prime, which we know is arcsecant of x over a prime, is equal to a divided by x times the square root of x squared minus a squared. QED, we are done. We got what we had said it was going to equal to start with. Awesome. So now hopefully you remember how to take the derivatives of inverse trig functions. That's all. Bye, guys.